Every major scientific claim starts with a massive population we want to understand, but we rarely have access to that entire group, so we rely on isolating a tiny handful of data, a sample. Because that sample only represents a fraction of the whole, absolute mathematical proof of any broad claim is impossible. This limitation means every scientific conclusion is built upon a measurable margin of error. To navigate this problem, statisticians developed a mathematical framework known as hypothesis testing. This system is designed to identify, quantify, and manage the exact probability of a conclusion being incorrect. Today, we will build the formal architecture of statistical inference from first principles. First, we will define the mutually exclusive claims that must trigger every statistical test. Second, we will mathematically map all possible outcomes where human decisions intersect with hidden reality. And third, we will define the probabilistic limits of making a catastrophic error. This architecture provides the formal criteria required to define the boundaries of scientific evidence. The architecture begins by distilling a real-world question into two opposing, mutually exclusive viewpoints. The null hypothesis, H sub 0, represents the baseline status quo and must always contain a condition of equality. The opposing alternative hypothesis, H sub A, is the contradictory claim being tested. It strictly prohibits equality, relying entirely on greater than, less than, or not equal to symbols. We can apply this to a test determining if more than 6.6% of U.S. students take advanced placement exams. The claim is more than 6.6%. Because that condition lacks equality, it becomes the alternative hypothesis, which automatically sets the null as less than or equal to 6.6%. These two hypotheses cover every mathematical possibility, establishing a logical foundation before we examine the sample data. Once the data is gathered, the researcher must make a choice between two valid actions. They either reject the null hypothesis, or they fail to reject it. We do not accept the null, because a lack of evidence against it is not evidence for it. Mapping actions against reality creates four outcomes. Diagonal quadrants are correct decisions. However, rejecting a true null hypothesis is a type 1 error, represented by alpha. Failing to reject a false null hypothesis is a type 2 error, represented by beta. This completed matrix shows that statistical error is not an operator mistake. It is an inescapable probability built into the structure of sampling. Since both alpha and beta are inherent risks, statisticians must evaluate which error carries the higher real-world cost. In an emergency room, the null hypothesis is that an incoming accident victim is alive. A type 1 error means concluding the victim is dead when they are actually alive, so the medical team stops treatment. A type 2 error means treating the victim as if they are alive when they are already deceased. Wasting resources on a deceased patient is a less severe outcome than failing to treat a living one. In scenarios where a false positive carries fatal stakes, the framework requires researchers to minimize alpha to protect the status quo. In other contexts, the mathematical priorities shift based on the physical consequences of an error. When testing rock climbing equipment, the null hypothesis is that the gear is safe. A type 1 error here means believing safe gear is faulty, resulting in the financial cost of replacing functional equipment. But a type 2 error means believing compromised equipment is safe. The consequence is that a climber relies on failing gear and falls. In this scenario, beta is the catastrophic variable, while the alpha risk is negligible. The 2x2 grid is mathematically neutral. The researcher must analyze the physical environment to decide which error poses the greater threat. We can now focus on the primary objective for most researchers, correctly identifying when the alternative hypothesis is true. This occurs in the bottom right quadrant, where we successfully reject a false null hypothesis. This correct outcome is called the power of the test. In a reality where the null is false, the probability of a type 2 error and the probability of a correct decision must add up to 100%. This defines the relationship. Power equals 1 minus beta. To ensure a study has a high probability of discovering the truth, the test must be engineered to minimize the risk of missing it. We live in a world where population-level certainty is out of reach. We address this by forging opposing claims and calculating the exact probabilities of our failures. To increase the accuracy of these tests, researchers increase sample sizes, which shrinks the risk of both alpha and beta errors. This framework standardizes how drug approvals and economic policies are evaluated, ensuring every conclusion meets a specific threshold of evidence. Hypothesis testing maps the specific risks of our ignorance, allowing for decisions that account for the exact probability of being wrong.